All right. Welcome everybody to the April 8th version of the CFAS General Meeting. My name is Wesley Clem, and I'm the president of CFAS and your host tonight. Uh, Tonight, I wanted to talk about if you're here, sorry, let's get this started. If you happen to be watching and you are not a member of CFAS, you should join. You should think about it. We have access to private events, our dark sky viewing locations in the closest dark skies we have to Orlando, anyway. We have our loaner scope program. You can check out telescopes from the club itself and hang on to them for a little bit and use them and view. We also have our remote observing program. We have a sea star out at the Starfront Observatories in Texas, and you can reserve time on it and check out what a telescope can actually really do in a dark sky. And we have examples of that to show later. We have our online community on groups.io where you can join and ask questions and interact with other members of the club. We have multiple different groups on there where you can talk about outreach, astrophotography, sea stars, and a few other things. We have our quarterly meetings out at the Seminole State Emile Bueller Planetarium at Seminole State College. What better place to have a in-person meeting, right, at a planetarium? We have a free Astronomical League membership where you get Reflector magazine. We are a nonprofit 501c3 organization, and we are all volunteers here. So every member of the board volunteers their time. So we do this because we love it. You also get discounts on Astronomy and Sky and Telescope magazine. So be sure to look into how to get that if you're not using that discount. On today's agenda, we have Justin Peatross. He's going to give a talk on integration. How much time is enough? And that is a question I ask all the time. I kind of just settled on 30 hours, and that's what I do. Follow that, we'll have a Q&A with Justin if you have any questions, followed by club news, upcoming events, and finally our astrophotography showcase. And then after that, the meeting will officially conclude, but then feel free to stick around and we'll chat with Justin as long as he has time. So on that note, Justin, I'll pass this over to you to go with your presentation.
Awesome. Thank you guys so much for inviting me. I really appreciate it. Let me go ahead and share the correct screen. That is one. All right. Let me know if you guys can see.
I see it.
All right. So, my talk tonight is about the integration, how much time is enough, the challenges and joys that come with long integration astrophotography. So, an extremely quick bio about me. I've been doing photography as a hobby for about 25 years. So I've been doing it for a bit of time. Astrophotography specifically about 5 years. If you do the math, you can figure out that I started late in 2020. You can probably guess why. Um, I've been a member of the Deep Sky Collective for a little over 2 years. I'm not sure the exact amount, somewhere between 2 and 3. The Deep Sky Collective is a group that focuses on extremely long integration times, like 400, 600, 800, 1,000 hours on targets. And I currently have 4 remote rigs. That gives me a benefit. It's a lovely benefit to have of being able to spend a ton of time on individual targets and still kind of churn through a lot of data pretty quickly. So, no stranger to nighttime photography. This is some older stuff that I did just for fun. I've been doing photography for a long time, but nighttime, like astrophotography specifically started kind of the beginning of COVID. I was told to go home, hang around to know people, and just needed something to do. I was not a fan of taking pictures of people, and as I ventured further and further away from where I live, that meant it got darker and darker and darker, which eventually meant, hey, nighttime pictures. So this little baby here was kind of my first setup, and I quickly realized that I enjoyed that, but I wanted to zoom in more. And one thing led to another, and I soon had a full-blown astronomy rig, and never looked back. Current setup's kind of the extreme ends of my field of view. So I have a Rokinon 135 camera lens. Technically, the field of view is at focal length is about 130 millimeters. And then I've got a Schmidt Cassegrain, which is a C11, which native focal length is about 2,800 millimeters. When I first started taking pictures, this is October of 2020. Like everyone, kind of find bright objects that are easy to do, and I just was so excited that looking up at something, and I could look at the screen and go, "Wow, that's there." Pretty quickly moved on to kind of dimmer and more challenging targets. This was the Pinwheel Galaxy, November of 2020, Andromeda, December of 2020, and then the Horsehead, and that was January 2021. At that point, I kind of slowed down just a little bit, um, not in the amount of pictures that I was taking, but the amount of targets that I was getting. I was starting to get frustrated with how noisy they were and how rough they were and how hard it was to get something good out of it. So I started doing research and figuring out that, hey, some people that say more integration time is better. Okay. So this was probably about 30 minutes. This was 10 hours. It was about a year later. So pretty significant improvement. And that kind of got me, okay, adding more time does make a difference. Switching to my C11, this is a few years later. This is 96 hours of integration time. And technically, I have, I think, another 50 hours of data that I shot on the same target after this that I need to go back and add. Um, that just, it opened my eyes to the fact that, hey, if you spend a lot of time, the really, really faint stuff, it stops being noisy. I think the biggest one that kind of opened my eyes for that was the IFN, or Integrated Flux Nebula, sitting around M81, M82, the Cigar Galaxy and or Bode's Galaxy and the Cigar. This is about 68 hours from a Bortle 4 location. And this was with a mono camera. So I shot luminance, red, green, blue, and then hydrogen alpha for the jets coming off of the Cigar specifically. I want to say that 35 hours out of that 68 was just luminance. I just wanted to get that dust. And I looked around at a lot of different images online. I didn't see stuff that looked like that. And that just, I was like, all right, this is what I want to do now. I want to find the stuff that's super, super dark, that's super hard to get, and I want to get it really, really well. Some of my experiments maybe were overboard. That kind of got me. This is just the core of Andromeda. This is 75 hours. This was such clean data. I did zero noise reduction on it. None. I moved right past that step because there wasn't any noise. And so I realized, okay, there is a possibility of overshooting. Moving on, this is probably the longest one that I've done that I've finished editing. I have more that are longer than this, but not are finished. This is a portion of the Great Lacerda Nebula. I did this late 2024, and this is about 115 hours. And then for challenging targets, CTB1, the Medulla Nebula, also called the Garlic Nebula, it's about 85 hours in hydrogen and oxygen. All right, so as I kind of dove down this path of just doing longer and longer integration times and trying to find fainter and fainter objects, I got invited to join the Deep Sky Collective. They are a group of amateur astronomers, astrophotographers that try and use telescopes collaboratively to capture images in quality and detail that is unrivaled. We want to be able to open up the astrophotography scene in a way that contributes back to science and allows them to get the most out of their equipment. We've had images published in the Chandra's X-ray Observatory website, a scientific research paper, as well as multiple awards, which I'm grateful to be even a small part of that. This was one of our more recent ones. This is supernova 1181 in the constellation of Cassiopeia. This is 882 hours in luminance, red, green, blue, hydrogen, and sulfur. In this case, this particular image, the blue is sulfur. If we switch to a more comfortable palette here, or not comfortable, just more recognizable, the yellow here is sulfur. This was the very first amateur image of this particular target. And then most recently, the Scylla supernova remnant, which if you happen to have been on Astrobin today, this is their image of the day. So this was discovered actually quite recently in 2025. And apart from the discovering group, only 3 other hobbyists have ever photographed this target. This particular one has 538 hours. So now that I've gotten all of that out of the way, what are our challenges? Well, the first challenge is, if we're going to take a bunch of pictures and we know that the total time is going to be really, really high, how long should each individual picture be? Um, it does matter. The unhelpful but technically correct answer is going to be as long as you can possibly get away with, from as dark a place as you can until you swamp your read noise sufficiently. And why? Um, so, sky quality. The darker the sky, the better your images are going to be. That's just a fact of life. All of the light pollution is washing out the signal that we want to get. So the darker we can get away, the less of that is getting in between us and the information that we want. Exposure length. The longer we do it, the better it's going to be. Each individual frame will be, and we'll get into the math of why that is and how we can optimize that. And finally, aperture. If you have a small bucket, you're going to get a small amount of light. If you have a really big bucket, you're going to get a lot of light. So, sky quality, go to a darker site. Exposure length, get longer exposures. And aperture, buy a bigger telescope. That's not realistic for a lot of people, including myself. I'm not just going to buy a bigger telescope every time I want to get a better picture. Go to a darker site. That's definitely a possibility. But sometimes where I'm at is as good as it's going to get. So the one variable I still have left is exposure length. I can always go longer within reason. Now, there are some downsides. Satellite trails, planes, all the other crap going through our sky that isn't what we want. Eccentricity, guiding issues. Mounts are imperfect. They don't work magically. They are mechanical in nature and they can cause issues. And especially if you don't want to spend tens of thousands of dollars on a mount, there's going to be limitations to that. And then finally, overexposures of bright areas. Your cameras have a finite amount of light that they can record before the sensors are full, and there's nothing left. So what are we looking at? Well, moon, really, really bright. So we're going to take really, really short frames. Pretty self-explanatory. All right. Faint nebulosity. Might need some longer ones. And then we get to challenging stuff like this. This is the Phantom Galaxy. It's about 90 hours on there. But even for the luminance, I have, I think, 3 different exposure lengths. Because the really, really bright parts, I get tons of signal really fast, and then it's gone if I go really long exposure. All of the IFN, all of the faint dust surrounding it, really, really dim. If I don't expose long enough, I'm not going to get it. Now to the fun technical stuff. Every picture, when we take it, is in a raw, unedited format, and it has just linear data. So, for a lot of astrophotographers, we use a tool called PixInsight. There should be equivocal ways of doing this in other tools. This is just what I'm familiar with. If you open a picture in PixInsight and you mouse over any individual pixel, there's going to be values down on the bottom, and it's going to show you how bright that is. By default, it does this really weird 0 is black and 1 is white. And so you get this really weird fractional value that makes it really challenging. If you change your readout option, and this picture I've got here to 16 bits, my camera has 16 bits. That's the actual pixel values that it can register. It's from 0 to 65,535. So if I mouse over that and I get a number, that's the value. And that makes it a lot easier to figure out what you're looking at. So take your cursor, point over an area, and you get a value. In this case, K equals 282. That does not mean 282 electrons. That's simply the value that are recorded. And unfortunately, we get to even more math. So if you go to your camera manufacturer's website, they should have, hopefully, something like this. This is a system gain chart. And it's going to tell you, here's when we receive signal coming in, when it finally gets recorded, what's the conversion here? So in my case, this particular camera has 6 different modes. We're going to ignore the first 3 because they're basically legacy, and the last 3 are the new ones that are optimized to have lower noise. They're basically identical except for lower noise. In my case, for this, the particular images we're going to work with, I use the extended full well mode. So it gave me the biggest bucket, so I could capture the biggest range. Unfortunately, that also increases the noise, as we're going to see. But in our case, I moused over the dimmest part of the screen or the image that I could find and found just where's background. Just as far as I can tell, there's absolutely no signal. well, but there's still something. We've got sky glow, we've got all kinds of other stuff, we've got light pollution, whatever. But that's the baseline. So what's that value? In my case, it was 844. Again, using that 16-bit value. And if we look at this chart here, we can see that it starts at 1.6 and moves all the way down to these really low numbers once our gain goes up. In my case, my gain was 16, which gets us to about 1.5. So if I take 1.5 and I multiply by 144, I get 1266. So that's just my baseline level. All right. Then I picked a couple other sample areas. One, a really, really bright area. This is a dim target, but it's a bright area for the kind of the main part of the target. And then I found kind of the faintest areas I could in that target, and I picked some sample values for that. So 868, which we can see is quite close to the 844, and 1076. Multiply those out and we get our values for electrons read. So that's actually how many electrons actually fired off. So 36 for the first example, 348 for the second sample. All right. And then we go to, we're going to go. There we go. Okay. Another of the charts. I feel like a lot of people look at these charts and we just move past them. They do matter. In this case, and I kind of shot myself on the foot here, I was using the extended full well mode, which if we look here is this yellow one, which has a really high read noise comparatively to some of the lower ones here, like the high gain mode. In my head, when I first shot this target, I was like, oh, the telescope I'm using is really, really fast. I want to get the biggest dynamic range. I did not do this math. And we'll see, I got penalized for it. So we can see here, it's about 5.5. So our read noise, the read noise is flat. It's just every time you take a picture, there's read noise in there. That read noise is random, but it doesn't matter how long the picture is. If I take a 2-second picture, a 300-second picture, a 900-second picture, the read noise is identical, which is why we want to swamp the read noise, because if we introduce this much, if I take a 2-second picture and I got this much signal, it's not much to work with. But if I take a really long one, I've got a lot more to work with. And our read noise squared is 30.25, which we'll care about on the next page. All right. More math. But I promise you, it matters and it's helpful. And hopefully, you don't have to do this too often. All right. So our baseline values, we've got a read noise squared. We've got our background that we measured. And our sky background, ideally, you'd like it about 10 times the read noise squared. In our case, we're way over that, even for the faintest areas of our background levels. So we're at a 41.8, and we really only needed to be at 10. So amazing. We have well swamped our read noise. We are no longer read noise limited. Cool. So we're done. We don't need to take a longer picture. Not so much. Remember, we only got 36 electrons in our first example and 348 for the really bright area. All right. Noise. So noise is annoying. It is a part of our images. It's just what we have to deal with. And the math here equates to the signal itself is also part of the noise. It is annoying, but it is what it is. So in our first example, we have a signal to noise ratio of about 1. Our signal to noise ratio on the bright areas is 8.6. So relatively, those are just numbers. That doesn't tell me a whole lot. For these particular images, I think they were all 10-minute exposures. So signal to noise ratio of 1. How long does it take to get to a signal to noise ratio of 20? A lot of people aim for 30 to 40 or higher for a really good quality image. All right. And I'm pulling up the chat here to answer some questions here. So how do we get to 1266, 236, and 348? Thank you. So let's go back just a second. That is a great point. So 1266 was our background value. So that's just the total amount of electrons we read in the signal when there was nothing that we could expect from the actual object. So just the background area of the sky. There's stuff coming through here that's not part of the target. So 1302 was kind of the faintest part of the target that I could identify as being part of the target. And if we subtract 1266 from 1302, we get 36 electrons. So for the dimmest part of the object, compared to the background area around it, was 36 electrons. And in the case of 348, it's 1614 minus 1266. All right. So thank you. And please, I'm going to move the chat up here so that I can see it better. If you guys are confused by something, please get my attention. Obviously, I'm on Zoom, so I'm not physically here in front of you all, so I can't see, which I do miss. So get my attention. I'm going to move this where I can see it nice and easy. All right. Let's go to back where we were. All right. So now the noise here, signal plus background plus read noise squared gets us the signal is 36. It's part of the noise. 1266 is our background. Our read noise squared is 30.25, which gives us a noise level, just a baseline noise level for the dim part where there actually is signal of 36.5 electrons. And for the bright area, 40.5. But we had 36 electrons that were just signal, as best as we can tell. Divided by 36.5 gets us just under 1. So our signal to noise is almost 1. Whereas the really, really bright part, we got tons of signal. The noise level didn't increase that much. So we 348 from 36, and we only bumped up by 4 electrons. So our signal to noise ratio went much, much higher. So signal to noise increases by the square root of the number of frames, which is pretty annoying because it means we need exponentially more time to increase our signal to noise. So for the dimmer part, which has a signal to noise ratio of roughly 1, it's going to take us just over 400 images to get to a signal to noise ratio of 20, which isn't amazing quality. It's okay. Whereas 6 images would have been enough for the bright stuff. So if you ever looked at a short integration time for a project, the bright stuff's going to be fine. It'll look great. The challenge is when you want to get the really dim stuff. That's the really noisy stuff. And the problem is because the signal is so low and the noise is relatively the same, your signal to noise ratio gets worse and worse the dimmer it is. If we had a signal to noise ratio of 0.5, we'd need 1,600 images to get a signal to noise ratio of 20, which is a lot more images. So in our case, 400 images at 10 minutes. I'm going to be incredibly lazy and just pull up a calculator because I don't remember the top of my head. So 400 images times 10 minutes gets us 4,000 divided by 60. Yeah, it's a lot of time. 60 plus hours. I did my math correct. Whereas obviously 6 images at 10 minutes a piece, that's an hour. That was nice and easy. So yeah, not fun trying to get the dim stuff, but that's just the reality of it. So with the Deep Sky Collective, we have 400, 600, 800, 1,000 hours on a target. That's why, is because what we're trying to capture is so incredibly dim. It just takes a really, really long time to be really confident that we have signal and not noise. So this was the image that I was sampling from. This is the Rokinon 135. This is in hydrogen, I believe, of the Veil Nebula and the surrounding region. So the Veil itself is actually pretty bright. And those samples, super easy to get. All of the faint stuff, not so much. So I'm probably going to need to go back and spend more time on this. So between the 3 channels, I had spent 60 hours. And I probably need to spend 60 hours per channel. Or if I hadn't done the high pixel value, the full extended full well depth, I would have had a lower read noise, which meant I would have gotten more signal compared to my read noise, and I would have gotten a better image. Lesson learned, I need to change my settings. All right, so longest possible exposure that you can without introducing things that you can't compensate for. So satellite trails in your images is fine to a certain extent, as long as you have enough images. If you're stacking 6 images and you have a satellite trail in one, that's not going to work. But if you have 600 images, it doesn't matter. Stacking algorithms will see aberrations of things that are obviously dissimilar to all of the other values and will discard those individual pixels while not rejecting the entire image. So if you have a satellite trail running through a single frame there and it goes, hey, these values are incredibly bright. I'm expecting a value of 60 electrons and I got 780. That's not right. And if I look at all of the images before and after, none of them have that value either. Okay, those individual pixels are bad. We're going to ignore them, and it just creates a mask, effectively masks out those individual pixels, and then uses the rest of the image. So, longest possible exposure that we can get away with without introducing eccentricity. So if you're guiding, your mount is struggling with guiding and your stars are getting oblong, you're smearing the data. Tools like Blur Exterminator, and there's a few other open source ones, are really good at recovering the stars, but they don't recover the underlying data underneath of it. So if you have distortion, there's only so much you can do to recover that. So ideally, you want sharp stars. And sometimes that means going shorter than you'd like. And as long as you've got high enough above the signal floor to get enough SNR that it's reasonable, then stop. If a 600-second exposure is more than good enough to get what you're after, don't go longer. Sometimes it's not. For the Deep Sky Collective, our minimum exposure length is 15 minutes. And ideally, if you can run longer, they want you to run longer. The official answer for pixel blowout for like stars, don't care. We can go fix that later by getting some small amount of much shorter exposures to recover those. But the signal that we're trying to get is so incredibly faint that we need every advantage we can get to, even under these extreme amounts of time, still get something decent. John asked if there's a minimum signal to noise ratio that we're trying to get for on the Deep Sky Collective. I'm not sure. The answer is always as much as we possibly can. So typically our projects are time-based. So we're going to say, hey, we've got 3 months, 4 months to capture our target. And eventually, it's not going to be visible anymore. We ran out of time. So the last one, Scylla, what was, I think, 10 imagers. And we got, 540 hours on it. The Supernova 1181, we had 800, but it was probably about the same time. Just depending on the season, depending on everyone's weather, we get more or less, but we're always going to shoot for as much as we possibly can, because better signal to noise ratio is never bad. Every once in a while, say, hey, we don't look like we have enough data. Let's spend another month on it. That's before looking at the data. That's just looking at the raw numbers. And you'll see why when I get to that portion of it. So hopefully that answers the first question, which is just how long should my exposure be? Second one is, how long should the whole project be? And here are some unhelpful but technically correct answers. A single picture that captures the target. You got it. It's there. It's in the picture. We're done. Move on. Infinity. Also a very unhelpful but technically correct answer. The curve for signal to noise ratio does not ever fall off. It gets steeper, but it never ends. And so you will always improve your image by spending more time. It takes exponentially more time. If you spent 900 hours on a project, that last 100 hours to go to 1,000, probably not worth it. It might be if you have an incredibly challenging target, but I highly doubt it. That 100 hours would probably be much better spent bringing another target up from a really crappy SNR to a good SNR. And so the final answer is it depends. It drastically depends on the target. I'll go back to the moon. This is just a random frame. I was looking through some of my sharp captures. That's 7 milliseconds. I got enough signal. I could have spent much more time to get like the Earthshine and that kind of stuff. But for the part that I wanted, a single exposure had enough signal. Looking at a C star, this is a S30 Pro, a 30-second raw frame. The only thing I did was debayer it and stretch it. No sharpening, no color calibration, no noise reduction, no nothing. I, I can just barely see a hint of the Running Man. I can see the nebula quite clearly. If I'm doing like a Messier challenge, done. I move on. I got it. But if we don't want a ton of noise, we're going to have to spend a lot more time. So I'm not going to reveal the object yet, but this is an actual, I did the math on here. What would the total integration time to signal to noise ratio? And if we look at that curve again, it never falls off. It keeps going up, but it keeps getting steeper and steeper. So, 2,000 hours gets us to an SNR of 100. But to get to 200, we got to get to like 8,000. Okay. We double the signal, quadruple the amount of time. It's just the math. And so the question becomes, is it worth it? At what point does it stop becoming worth it? Here is the Orion Nebula I did. It was back in February of 2023. This was 10 hours and like 11 minutes. I could probably spend a bit more time, and I actually have reshot this again. I haven't processed it on some of the fainter stuff around the edges with a lot more time. The center does not need time. I actually had to go back and reshoot it with a different telescope because I blew out the core. Everyone's favorite mistake to make on that. Ended up doing, I think, 1 or 2 second exposures with my Schmidt-Cassegrain because I'd already swapped telescopes. So even with that, and even reduced, it's like f7, so not a particularly fast telescope. Those 1 second exposures, this is the luminance channel. I had an SNR of 100 in under a minute. That's crazy clean. I don't need any more. I think I spent 2 minutes, a little bit more than 2 minutes per channel, and that was mostly just because I wasn't sure how many images we're going to have to throw away, because constantly moving the camera around and doing that kind of stuff at super short exposures and telling it to do stuff, I was just afraid of the telescope kind of bouncing around and getting poor images. So it's like, all right, just get a bunch just to cover things. I know I don't need it from a signal perspective. I just want to cover the bases in case I get some bad ones. Now, 120-second subs and some of the surrounding regions. We're just a relatively bright portion of it, but now we're talking about, well, if I want that signal to noise ratio of 200, which is way too much. I'm looking at 15 hours. If I want a signal to noise ratio of 300, I'm looking at 40 hours. Whereas if we go back to get a signal to noise ratio of 400, I needed 6 minutes. 6 minutes, 1 second exposures, 40 hours on 2-minute exposures. Again, just because the difference, the value of that, how bright that object was in the center versus the edges. That's how it dictates it. What about really, really dark objects? So here's the Squid Nebula and the bat surrounding it, or a portion of the bat. So this was a total of 120 hours. The HA had about 50 hours, and the O3 had 70 hours. However, the hydrogen is way stronger. The signal to noise ratio on the hydrogen was about 70. The O3 had a signal to noise ratio of just under 20. So I spent 70 hours on O3. I got a signal to noise ratio of 20. I spent 50 hours on HA. I got 70. If I wanted to get just from 20 to 30 on the oxygen, I'd need to spend a total, so 70 plus, I needed a total of 188 hours. I had to spend more than 100 hours just to get from 20 to 30. If I wanted to get to 50, 525 hours. And if I wanted to get a signal to noise ratio of 70, so to match the quality of the hydrogen, to get the squid at the same level of quality, I would need to spend 1,000 hours. I'm not spending 1,000 hours on one channel to match the quality of 50 hours in the other. I'm not going to do it. However, as I was doing this and I looked at the math and went, if I do a total of 188 and I've already done over 70, that's just 100 more hours. I might go back and do that. For this example, this was shot from a Bortle 1. So this is a remote telescope and a remote hosted facility. The Orion one was not. That was a Bortle 4. Here is the unedited, just I remove the stars and a screen stretch. There's no noise reduction. There's no nothing else. But that's the relative quality of the data. So pretty good. That's a signal to noise ratio of about 70 in the brighter areas. And obviously towards the outer edges, I'm sure it's much lower. However, even for the brightest parts of the squid, still just an SNR of 20. And it's much, much noisier So if we zoom in on part of the HA, very clean, very little noise patterns. If we look at even the bright areas of the O3, super, super noisy. So here's our chart here, total integration time. In my case, I did about 50 hours on HA and 70 hours on O3. But you can see here, curves are the same shape. They just, yeah, it's painful. All right, let's move on to, yeah, this is what it actually looks like. So, obviously, if we're looking at this image, this is a nice looking image. But I'm pushing the oxygen way brighter than it should be, because again, we've established hydrogen is really bright, oxygen is really, really dim. We're going to push the O3 quite a bit more just so it stands out. I'm not making up signal, we're just boosting it so it's visible. If I were to stretch them equally, that's what you get. I can barely see it. And spending more time isn't going to fix that. It's going to be cleaner. It's still going to be dark. So there's our squid. If I wanted to do 1,000 hours, I get past 70. And if we went all the way to 10,000 hours, now we're getting close to the M42 levels of quality, which is not realistic. I'm not spending 10,000 hours on a single target ever. All right. Briefly, I'll touch on Bortle. So, and John did mention that. So, this was image from a Bortle 1 zone. It's about 30 hours of data, and it's a mixture of short, medium, and long-ish exposures. This particular telescope, I've got some work to do to be able to do longer ones. I'm having some issues, so I'm actually limited by my mounts issues. I can't go more than about 5 minutes. So I would really like to get longer than 5 minutes because the really faint parts of the IFN, I'm not getting the signal to noise ratio I wanted. However, if I were to shoot this from a Bortle 4, it's much worse. That, especially the fainter areas, I'm not going to get that. I'm going to have to work much, much harder. So if I wanted a signal to noise ratio of 40 in Bortle 1, it's going to take me about 15, 18 hours. 40 all the way over here gets us to past 50 hours. So 15, 18 to 50, quite the swing. So as much as you can, find a spot that you can safely image from that's as dark as you can get away with. Luke asked, how do the colors in these images compare to what our eyes would see if we were actually floating in space? I'm not 100% sure. The colors would be decently accurate. The problem is that obviously if you're floating near them, they're going to be so huge you won't be able to see them, just a small portion of them. Oxygen is probably a slightly more teal than a true blue, but those colors are relatively true. Obviously, we start throwing sulfur in there, we're going to have to start picking some other colors because both hydrogen and sulfur are red, and red on red doesn't give us a lot of clarity on what we're looking at. All right, quick tangent between our challenges here. How much storage space is this going to take? The answer is a lot. This is another reason why long subs are our friends. Obviously, if I take a 15-minute picture and it takes 40 megs, and I take 3 5-minute pictures, that takes 40 plus 40 plus 40. That's 120. So I took 3 times the amount of space to get a slightly worse version of the same image. That's not great. Size depends on how many images you take and how large each image is. So if you have, an APS-C sized camera, you're going to have a specific size. If you have maybe a micro four thirds camera and it shoots in 14-bit instead of 16-bit, well, your files are going to be much, much smaller. If you have full frame, medium format, the sizes get bigger and bigger and bigger. So even if I have like this Hart Nebula is 104 gigs for 45 hours at 5-minute subs, whereas the Veil is 16 gigs for 60 hours, 10-minute subs. Even if we pretended they were 5 minutes and doubled that at 32, they're still nowhere close to each other because those particular cameras, wildly different file sizes. And that, unfortunately, is just the initial storage requirements. When you're pre-processing the data, you're going to end up with 4 to 6 times that amount. So I was doing... for the Deep Sky Collective, we have a ton of different people taking pictures. Their field of view should be relatively similar. Their pixel scale should be really similar. That's kind of the bigger thing. but we've got hundreds and hundreds of hours of data to stack. It's not uncommon to have 800 to 900 gigs worth of just calibrated frames, and then I've got to stack that. And 800 to 900 gigs, then 4 to 6 times that, you're looking at 6 terabytes worth of data you got to work with. It takes up a lot of space. And then you ideally would like to hang on to the raw data for as long as you possibly can, ideally forever. I don't delete old images ever. Every raw frame gets saved. Every flat frame gets saved. Every dark frame gets saved. Every bias frame gets saved. You can always go back and reprocess something, but if you've stacked to your integration and then thrown away everything else, that's an encapsulated object. You cannot do anything else to that except proceed forward. You can't unbake the cake, if you will. When you add time to a target, let's say you spent 30 hours on it this year and you go, I want to try and add some more time next year. You got to have the raw frames to go back to add to it. The software is going to be doing comparisons between each frame to determine the best value. And if you handed it one that's finished and then one that's a single frame, that they're so different, it's not going to be very useful. You're just not going to get the same value out of it. So, in addition to that, new pre-processing techniques or tools may increase the quality of those stacked images. I know SETI Astro Suite Pro has some new tools for stacking that have supposedly increased the quality a little bit for some targets. That's something that I would like to test. Haven't had a chance to do that yet because it's pretty computationally expensive. And all of my projects are really long. But I'm going to do it to see, hey, if it gets me a 5% improvement in my quality, 100%, let's go. But I can't do that if I already have a finished stack and nothing else. Or what happens if you stack everything and you just go, all right, I don't have time for this. I'm going to do this later. And then you go to edit it and something's wrong. I've had stacked masters that had some miscalibrated flats in there. And so I had these giant dust motes sitting in my images and I couldn't use it. So I had to go back and find the wrong ones, find the mismatched flats, delete those specific ones and redo everything. If I had deleted all the old images, I was up a creek without a paddle. Now, one very, very obvious downside, storage space. I currently have over 20 terabytes of astro imaging data and counting. It's not going down anytime soon. I have some thoughts on maybe trying to figure out if I can keep just stacked flats, but that means I've got to look through every single flat and make sure that they're all good. If I'm lazy and I don't, then if I run into a problem, I can just go do it again. But at a certain point, I might have to because it's a lot of data. All right. I'm going to move quickly through the last bit of stuff. And then we'll take some questions after that. The third challenge, how much compute time is this going to take? Be patient. The longer the target is, the longer it's going to take to stack. That's just pre-processing. Obviously, if you're blinking through hundreds of images, that's going to take some time. Organizing everything, moving things around. If you realized, I need 800 gigs of space just to run the tool, I'm going to need to go clean up drives and move things around so I can even do that. On an individual target, the longest I've ever spent was about 20 hours. My computer just sitting there with me, not touching it, just running stuff. For a group project, that's well over 60 hours. For our Deep Sky Collective stuff, we cannot use automated tools like weighted batch pre-processing. We need to have our hands in every single piece of that, every step of that. So weighted batch pre-processing is an amazing tool by PixInsight that just automates giving all of the raw data, filtering through it, cleaning up, organizing it, and stacking it. Unfortunately, when you've got 800 hours worth of data, you want to get the best possible quality. And that means doing step one, then looking at the results and evaluating, then doing step two, then doing step three, and then doing step two again because you didn't get the results you wanted. So that 60 hours is just compute time. It's like a full work week and a half, just working on it. So my computer's busy. I'm busy. I will say this, Deep Sky Collective, they do have a tutorial on our pre-processing. So there's a whole big article on just like, hey, how do we do things? This helps us internally be consistent about making sure that we are turning out good quality results, but also helps any other group or individual processor who wants to start working with really deep data sets. How do you get the best possible quality out of that? So we've got whole matrices of how to get the best out of it. And especially when you start working with group projects and you have different telescopes that all have different kind of distortion fields and aligning everything and making sure that all matches, how do you get the best out of it? Stuff like this. But at the end, hopefully it's worth it. A couple of recent longer ones. This is M17 I did in 2024. It's about 68 hours. There's the Monkey Head, which is 86 hours, again in 2024. And then again with Rokinon, that's only about 45. But I wanted to get first light on it, and I wanted to go quick. And for me, quick is 40 to 45 hours. That's like my bare minimum. So hopefully that was entertaining and enlightening. At this point, I'll be glad to take any questions for the remaining time that we have.
Wow, Justin, that was awesome. Yeah, we did have a couple questions come in.
Yeah.
Frank had a question, and it's actually the same one as me. How do you go about integrating data from different telescopes with different characteristics? Is there some like it has to be within like this margin and this margin?
Um,
Because obviously, like merging like a red cat with
right.
a C11.
Yeah. So ideally, you're going to want your pixel scale to be the same, or as close to it as you can. So if you have wildly disparate fields of view, probably not going to be super useful. However, if you have that, then you can either drizzle the smaller data and scale it up, which drizzling is amazing. I didn't really talk about it, but it does decrease your signal to noise ratio by a factor of 4 if you're doing 2x and by 9 if you're doing 3x. So like the Rokinon 135 is wildly undersampled. I really should be 3x drizzling, but I don't want to because I don't want to spend 9 times the amount of time just to get the best possible data. It's just ridiculous. I'm not going to spend, if I want to spend 60 hours, I'm going to have to spend 60 times 9. I'm not doing that. So you can do that. You can either upsample your lower quality as long as you have a high enough signal to noise ratio, or you can downsample the larger one. So if you have one that's super, super zoomed in, you go, all right, I'm going to sacrifice that resolution. I'm going to increase my signal to noise ratio, and I'm going to scale it so that it's appropriately sized to the smaller one. For the Deep Sky Collective, how we solve that is we have 2 different groups, kind of subgroups, and some people are in both groups. We have a small field of view and a large field of view. And so the requirements are like, hey, you must have, a resolution of this many arc seconds per pixel for this field of view and this field of view. And as long as you can cover the target, you're golden. If you're wildly outside of that, sorry.
Do you crop the to what the smallest
Yep.
telescope was? Just
Yep.
so that like you don't have some sort of different noise profile on the outer edges
Yeah.
versus the inner. Yeah.
Yeah. Because if you have different fields of view, then you're going to have differing signal to noise ratio.
Yeah.
And that's where you see those really hard lines is because not because they're 2 different cameras, but because you have such a difference in quality. So that hard line is usually from this part has the combined data from everyone, and this one has,
Yeah.
some or almost none. So it is quite common for us to trim because you have people that maybe have like the exact same resolution, but someone has a bigger camera. And they don't want to like have to go into the settings and crop every single image. They go, well, maybe I actually want to use the data for myself later. So I'm just going to give it to you guys and you guys figure it out. So we'll plate solve every single image. We'll spline align every single image to each other, and then we're going to pick a field of view, generate an artificial star map for that, and then align everything to that.
John Pinto asked, is there a difference between taking 10 subs at 10 seconds versus 1 sub at 100 seconds?
Yes. Yes. So the short answer is if you're getting above your read noise, that's step number 1. If you don't swamp the read noise, you have a horrible signal to noise ratio in your image, and you won't potentially even get the data. And then the second step is the signal that you're trying to get. How far above the background, kind of noise are you? So I had that one where we were looking at 36 and 348, and 36 had a signal to noise ratio of 1. So for every 1 electron worth of noise, I was getting 1 electron worth of signal. So that's okay. But if I got 3 to 1, then every image in 3 to 1 is going to exponentially be better for me as I stack together. Now, there are obvious downsides. If I'm on a tripod, I'm not going to be able to do 300 seconds or 100 seconds. Even with a Roku 135, I couldn't go longer than 2 seconds on a tripod. And that was with a full frame camera with really big pixels before I started getting star trails. So if you can't get good images with long pictures, long exposures are irrelevant. You work with what you can, but you want to get as much as you can to try and get the best possible quality in each image.
And would that be, I would assume that wouldn't be true across the entire Bortle scale. So like uh what you
You're
said
going
is
to
absolutely
be
true in like a Bortle 1, but if you were in a Bortle
sure.
9, 10
Um,
seconds versus 100 seconds.
yes and no. So you still want to go as long as you can. The problem is you hit the other end of the spectrum of maxing out your sensor.
Yeah.
So the sky quality is the sky quality. That's part of the equation that doesn't change, and it's going to increase at the same rate as your signal. So you're not going to get a benefit from that perspective, but you're also not losing anything from that perspective. What you do lose is when you run out of values. So if it's so bright that every time you take a picture for more than 30 seconds, you get a ton of white pixels, you went too far. That that's just the limits of your skies. And the answer to that then is, if you can, go to darker skies. You can't always,
Right.
and all that means is it's going to take exponentially longer. That you're fighting against, again, just signal to noise. So if your noise is really really high and your signal is really low, it's just going to take exponentially longer to get it.
Yeah. I hear you. I think I'm in a Bortle 7
Oh, I'm in a
and
9. I
yeah,
don't take pictures from home. It makes me very sad.
nice. Yeah. I've been to a couple star parties in the last couple of years and I just couldn't believe how much better my
Yes.
images were in like 6 hours versus
Yes.
like my minimum at home is like 20 to 30 and
Yeah. Yeah.
sometimes they're junk.
The first time I went from I would say I was visiting like Portal 5, Portal 6 to a Portal 3, I got lost. I went to Polar Line and I waited too long. I couldn't even find Polaris.
Yeah.
I was just like,
Yeah.
I can't find any of the constellations. I don't know where I'm looking at. I'm lost. I didn't grow up doing astronomy stuff. So I did not have that background of just knowing the sky. Like I had glow in the dark stickers when I was a kid on the ceiling of stars. I thought that was cool and I liked space, but in college and high school and all that stuff, I didn't really pay attention to that kind of stuff. So I didn't have that knowledge set. So when I looked at it, I was like, I'm gonna use my phone, and even then, I'm still not sure. There's just too much stuff there, which is why I'm incredibly grateful for computers and plate solving.
Exactly. Uh, John Starr asks, how do you select your targets?
That's a great question. For me, there are a few different criteria that I'm looking for. One, I want to find something challenging. I always look for something that benefits from really long integration times. Maybe the core part of it's been done to death, and that's fine. Like I did the Veil Nebula, and I spent like 70 or 80 hours on it, on a narrow strip of it too, because it's with a relatively zoomed in refractor. But there's a ton of faint nebulosity that's still part of the veil that's surrounding it that no one ever gets. If you look at it, it's just black there, and
Yeah.
that's because they didn't get enough data and they just crushed it to darkness. And I went, all right, I want to see what's there. And so I soaked a ton of time on it. And I was like, oh, there's a lot of stuff there that I just couldn't see.
It's like
Um,
exploring, sort of.
100%. That's what I
Yeah.
love. Like astronomy and astrophotography in general is about like looking into space and seeing nothingness and then going, no, there's a ton of stuff there. You just can't see it. Um, and then I get to go the extra mile of, hey, there's even more than you thought. It's so fun looking at popular targets and finding tiny little nuggets of, oh, there's a tiny little galaxy over here that I never saw before. Oh, the Rokinon field of view of the crescent, there's a tiny supernova remnant in there.
Yeah,
I
there's been
did.
a bunch of those in the last several years of
Yeah.
SNRs that just popped up because
Yep.
people decided to go deep on something. It's
Yep.
like, oh,
Yeah.
there's something there.
Yeah,
Or
it
that
took me a while to find it, but it did exist. Someone had discovered it before, but it's like, hey, it's not a common object because it's super super dim.
yeah.
But it just popped because I spent enough time to do that. The other thing, of course, is it needs to be up for long enough. Otherwise, it's incredibly challenging. Like I'm not gonna do Omega Centaurus. For me, it's not high enough. It barely clears the tree line. Like I just can't get it. And I wouldn't be able to do it justice. Obviously, there's targets that don't rise above the horizon at all for us. Um, but if I can get it, and I have no problems going multi-year, I I don't care. If a target takes me 3 years to do justice, that's fine. I I don't shoot one target at a time. So because I have remote rigs, I'm really lucky. I can use automation. So I use Nina to control my telescopes, and then I use a program or a plugin called Target Scheduler. And so I give it coordinates and I give it requirements. I say, hey, I'd like so many pictures of hydrogen alpha at this level exposure, and you can only take it when it's away from the moon by this many degrees or more. And for luminance, you may never take a picture when the moon is up. And I just tell it to go. And so I give it all these criteria. If this one's really important, I need you to hurry up on this one. This one is not important. It's a back burner target. So if you have nothing else to do and you're twiddling your thumbs, go take pictures of something. But it's early in the season, or it's just not as important to me. Go. And so I just start scrolling through things. And I find interesting pictures. I'll look through social media and some picture, and I go, I've never even heard of this target. I'll add it to the list. Let's look at field of view. Does it match one of my setups? Yes, cool. Let's add it to the list. Am I too late in the season? Okay, let's put it on the bucket for next year. If it's early in the season, let's go. So I don't have any particular like catalog that I'm trying to get through. It's mostly just, hey, what's up this time of year? What's interesting? What's something that I haven't shot or haven't shot well enough? There's certain targets that I've done, like the horse head, I've done multiple times. Technically, I've done it 3 times more since then. Um, I did it with the C11. I have a ton more time on that. I did it from the Rokinon, so I have the horse head and the Orion and all the other stuff around it in 2-panel mosaic. And then with all my telescopes, I did a 2-panel mosaic as well, just because I wanted to. And the last time I done it was several years, and I was like, hey, I think I can do better. And so that's what I'm gonna do. I saw a couple more questions come in.
Pete asked, I understand there is a C-Star collective that
Mhm.
captures long integration images. Is the difference between C-Star and higher capable rigs a matter of integration time, assuming all their factors are the same?
I have 3 C stars, and I think 20 hours is like my goal for a C-Star. What I will say is that is incredibly painful. So I have wedges for my C-Star, so they're in equatorial mode. The problem is, even so, the C-Stars originally, of course, were never designed for that. And so there are limitations. So we're fighting that really rough signal to noise ratio of really small aperture, really short pictures, and noise. It is what it is. So each individual picture is contributing less data than we would like. And then you end up with thousands of pictures to stack. It might take hours on a decently powerful computer to stack it because there's just that many pictures that's got to make its way through. Inherently, there's no difference between a C-Star and any other telescope that you were to build with the exact same specifications. The limitation primarily is exposure length. You're limited to 30 seconds, 20 seconds, a minute if you're perfectly aligned and you get really lucky. The problem I had with 1 minute exposures was I just kept having to throw out too many subs, and that was really frustrating. Um, for Jeff, I don't have enough time for 40 hours. I use smaller sub exposures. Um, can you still capture lots of details and faint nebulosity? You can still capture lots of details. That's absolutely possible. You work with what you can. Obviously, I'm incredibly grateful that I have kind of the setup that I do that allows me to get that enough time. I have one setup here, and the weather here is garbage. So for me, if I want to get one target for a season, that's all I'm gonna get. The weather is crap. We joke that we get our once a month clear night. That severely limits the amount of time that I can get for a target. And so if the goal is the best possible image, you're going to spend more time. If the goal is to get a great image that you're proud of, that's however long it takes for you to be happy with that result. I think I felt more joy over my 30-minute integration times than I do on my current ones because of just the sheer wonder. And I can't experience that again. Like my first time looking through a camera at a deep sky object on a dark sky and just going, holy cow, this is amazing. Like I practically cried. Like it was just amazing. Um,
I still keep that image on my phone. My
yeah.
first flame nebula. It's like, holy crap, it's garbage now. But like you
Oh, of
look
course, but you
back and
don't
you look
care.
at
Like
it's
that memory,
yeah.
like that, like so don't ever be like this is, pie in the sky. What could I do if I had unlimited time, money, budget, and clear nights? How do I get the best possible image? Within the confines of whatever time you have, you do the best that you can. Shorter sub exposures might be necessary to just combat sky glow because you're overexposing every single image. So be it. I, I Quiv, the lazy geek, he's a YouTuber, and he images from Tokyo, Bortle 9, and he turns out amazing images. You work within the confines. Like obviously, his individual frames suffer for that. It takes him much more time to get the signal to noise ratio he wants. Um, you use narrowband filters to cut through stuff for nebulosity, things like IFN. You got to go to dark skies. There's no way around that. There's some stuff that is just getting drowned out. If I point a flashlight at you and tell you to read the text on the back of it and I turn it on, you're not going to be able to do that. It's just not going to work.
Yeah.
But if you had a filter to cut it out and you could see it, you can. Um, so 40 hours is my personal minimum for most things. I recently did one that I spent 5 or maybe 6 hours on because I had a single night. It was an NGC galaxy that a supernova had blown off on, and we're like, hey, we've got like a week maybe before this disappears for us. And knowing our skies, they were crap except for one night. So I had exactly one night to capture it, and the moon was up for half of it. So I shot the hydrogen while the moon was up, and I shot everything else when it was down. That's all I got. I'm still really proud of that image as one of the shortest integration times I've ever done. I captured something that was there for a moment and then is gone. That's and it turned out fine. Would it have turned out better if I'd spent 10 times or 100 times the amount of time? Of course, but I didn't have that. And so I did what I could with what I could. And also not from Bortle 1 skies, Bortle 4, 4.5. Um, hey, yeah, I'm not going to beat that to death. You spend as much time as you can to get the best possible quality that you can. You expose each individual image for as long as you possibly can while not compromising the quality of that individual image. If you get bad pictures, you're going to get bad data.
Awesome. And with that, I think I'll thank you so much. I can't wait to continue after the meeting, but
Awesome.
in the interest of time for the rest of the meeting, for the recording, I think we're going to go ahead and move on. So thank you so much, Justin. Appreciate that. All right, let me get the slideshow started back up. Okay. Go. All right. On to club news. Um, uh, Tentatively this weekend, April 10th through the 11th, we have our Geneva Dark Sky Nights. I have checked the weather. They're looking okay, I think. So keep an eye on groups.io to see if that is definitely called or not. Usually someone posts on groups.io by tomorrow or sometimes Friday, but usually tomorrow, the Thursday, to let us know if that's a go or not. So keep your eyes on the forum. April 17th, the next weekend after that, is another dark sky night, again, weather permitting. We still have our remote sea star, of course. Please get on the groups.io subgroup, our remote observers, and contact Pete Lefebvre. He will get you hooked up with that, go through a short a learning process on how to use it, and then you can get that remote sky time out in Bortle 1, what Justin was just talking about. Like that Bortle 1, so much better than our Bortle 5 to 9 skies that we're used to here at home. And if you're not on Groups.io, please get on there. It's definitely where all of our announcements are. It's where our calendar is. It's where the community is. And you can ask for help and discussion and all that stuff. So if you're not on there, please check it out. May 13th is our next general meeting, tentatively. It's with Giovanni Linguito, and he's going to be talking about radiation in space. So hopefully that'll be when it is, and it's sure to be an interesting one too. So I'm looking forward to that. And also, just as a reminder to the club, we are no longer accepting checks. I know we've mentioned it a couple times, just a friendly reminder, we're not accepting checks anymore for the membership or any of the other things involving club payments and stuff like that. Upcoming outreach events. We have the Wesley Christian Academy, the wildly important goal party on April 14th. The Boy Scout Troop 200 KPP observing opportunity on April 18th. April 21st, Liberty Middle School STEAM Night. April 22nd, the Lawton Elementary School Lesa Garden. April 23rd, the Rosemont Elementary School, pardon that. April 29th, Redbug Elementary. April 30th, Spring Lake Elementary. And if any of these sorts of things interest you, please go and check out, again, groups.io, plug once more, to join the subgroup for outreach. If you have not participated in an outreach event, I highly recommend it. It is so satisfying to have a 6-year-old girl, an 80-year-old man, and everything in between take a look through your telescope and check out Saturn, Jupiter, or maybe the Pleiades for the first time and get that wow. It's so rewarding in this hobby. Taking pictures, doing astrophotography, that's rewarding too, but sometimes getting that wow from someone that hasn't seen it before is just as good. It's amazing. Um, and then Doug, if you are here, please feel free to speak up. You had a few words to say about outreach. Doug Woods is our outreach chair, and I believe he's here. You there, Doug?
If he is, he's on mute.
Okay. Well, Doug, if you are here, feel free to speak up anytime, but I'm gonna go ahead and move on. All right. New members, be sure to check out your welcome letter. You would have got an email as soon as you joined, and it explains how to get on groups.io. It explains those benefits that you get, which include like the loaner scope program, the remote C-Star, as well as where and when some of our Geneva dark sky nights are. And if you have any questions, please feel free to contact our board member at large, Denise Woody, at bmal2 at cfas.org, or contact me, president at cfas.org.
Hey, Wes, can you hear me?
Hey, there you are, Doug.
Yeah.
Yeah,
Boom.
I've been here. I've been struggling on my dopey phone in a unfamiliar interface to unmute myself.
Very good.
Um, I just had two quick items relative to outreach I wanted to bring up. First was the April 18th Troop 200 event. That is at Kissimmee Prairie Preserve. If anybody wants to go out there and experience Bortle, not Seven Skies, we should have a pretty good evening. And of course, if you would care to stay on a bit afterwards to, have another look around, feel free. Pardon me. The second thing is we've received a request from Fort Christmas Park, which is in Christmas, Florida, oddly enough, to do a series of observing events with their summer campers. That's on 8 different nights. Were they Friday, Wes? I think I said they were Friday. I think they're Friday nights. 8 in June, 8 in July. I think the only weekend when they're not doing anything is Independence Day. So you might want to keep that in mind. If you are interested, feel free to get in touch. I am retired. I'm too old to do 60 hours observing on anything. I don't have that much time left. But I'm looking for anybody who is willing to join up for those events. That is it. Thank you.
Awesome. Thank you, Doug. Yeah, if you are interested in any of those things, please get on the groups.io for the outreach subgroup. All of these events should be on there on the calendar. And if you go on there on RSVP, that's very helpful to Doug to know who we've got going to what. So thank you, Doug. All right, that's the new members. All right. If you are at all interested in helping out the club, we would really appreciate it. Again, there's another plug for Doug and the Outreach Committee. If you are interested, feel free to reach out to Doug there, outreach@cfas.org, to contribute anything that you can, any of your time. We're always in need. Um, Also, we are looking for another board member at large. As you know, John Frank resigned from his position as board member at large to focus more on personal and life stuff. So we are looking for a replacement. So if you are interested in helping out the club, having a vote on the board and attending board meetings, and being a liaison between the membership and the board, reach out to me, please, president@cfas.org, and let me know. We are seeking help. We are also still looking for a programs chair. Um, we had our previous programs chair, Sharifa Gassel. She has stepped away to focus on all of the awesome things that she's doing with NASA. And we are looking for somebody to help with programs. So scheduling speakers for our meetings and coordinating the speakers and stuff like that would be one of the primary goals. And you get a vote on the in our board meetings. So if you have an interest in that, please reach out. Again, president@cfas.org. Every committee in the club could use a helping hand. So if either of those things are not interested for you, but you do have an interest in like events, outreach, treasurer, loaners, science, website, membership, observing, education, or sponsorship, or if you have some other direction you want to take the club and have an interest, let me know, and we can try to make that work. We are also still seeking mentors for our mentorship program. We're still working on that. It's still in the works. Any specialty is welcome. So between astrophotography, visual, sketching, anything you like, if that's your thing, let us know, and you can become a mentor for somebody else in the club. Or just want to help in any sort of way, please feel free to reach out to Denise, bmail1 at bmail2@cfas.org, or me, again, president@cfas.org. We are a 501c3 organization. Again, I mentioned that before, that we are a nonprofit, so all donations are tax deductible. We're always seeking sponsorships and corporate donations, and we are on cyber grants. So some corporations do match donations that participate in the cyber grants program. Some upcoming astronomical events. I think most of us here probably have been paying attention, but maybe some new members or beginners haven't been, but definitely we're watching Artemis 2. I know I was a couple days ago when it was doing the lunar flyby. Man, that was so awesome to I'm too young to be around from the Apollo days, so this was really cool for me. I really enjoyed watching that all day long. So again, that on April 10th is the splashdown time that be watching. I'm sure if you're able to, that should be fun. April 9th through the 10th is NEAC, the Northeastern Astro Imaging Conference. Our own Richard Wright, I believe, is doing a presentation there. So be sure to be watching Astro News in some sort of way, that there'll be new product announcements, telescopes, cameras, stuff like that. ZWO is probably going to announce something. Skywatcher's got some stuff on the docket, so keep an eye out for some new stuff coming from our favorite brands. And then immediately following 11th and 12th is NEAF. It's the Northeastern Astronomy Forum. Again, all of our favorite brands are there doing their stuff. Usually that's when they announce new products, so keep an eye on that Astro News. April 17th is the new moon. If there are no clouds, please, that's the great time to get out there and take a look at stuff, image stuff. So around that time. April 19th, the moon, Venus, and Pleiades are going to be very close together. That might be an interesting astrophotography chance. And a good chunk of the middle of the month, the 15th through the 23rd, there's going to be an early morning planetary parade of Mercury, Mars, Saturn, and Neptune. And specifically on the 15th, the moon is going to be close there too, which could be a cool imaging chance. April 22nd through the 23rd is the Lyrid meteor shower. And on April 27th, roundabouts there, Comet C25 R3 Pan-STARRS is making its closest approach. I believe it's supposed to be naked eye, if the one thing I read is correct. So be sure to be looking in that direction, find out where it is in the sky, and take a look for it. Your phone probably can pick it up pretty easy too, or a sea star. And finally, the thing we all look forward to, the astrophotography showcase. And this first one, okay, this isn't from the club, but these were just a couple images from NASA. I thought they were cool. Look at that. It was, I think this was when just before they went behind the moon. That moon rise, right? The Earth rise right there. That was so cool. I thought this was a really awesome image. And then the eclipse when they were behind the moon from the sun. I just thought this was a really cool looking image. The composition of the moon and the sun illuminating the background. I just thought it was really awesome, so I included that. Next, Sharifa Gassel. Is she around? Are you here? I don't see her in the list, but Sharifa, she was very close to the launch. Had some really good shots of the launch there. So those are very cool. Close up of it. And then she actually took a video. I think this was with her Sea Star. I'm not really sure, but be sure to check out the actual close up of the launch. Nice. Never get tired of seeing that. Very cool. Thank you, Sharifa, for submitting those to me. Next up, we have Bradley Plummer. Are you around, Brad? I don't see you on the list either, but he also had some images of the launch. If I recall, I think his email said that he was in Cocoa or somewhere near there to get some cool shots of the launch from a little bit farther away. Super cool. Thank you, Bradley, for submitting those. Right. Steve Alderson. Steve, I don't see. Well, here you go, Steve. This was taken out at Geneva of the Rosette Nebula. I believe he was taking this with Skywatcher's relatively new little scope. It's like I think it's called the HAC 125. It's a little bit bigger than like a coffee can. It's really a cool looking little scope. It's one of those that has the camera in front of the objective, kind of like a Rasa. So very cool image, Steve. Thank you for submitting this. I was hoping that you would. I wanted to see a good sample of what that little uh, telescope can do. All right, Luke, I know you're here. I saw you. There you are.
Yes.
Cool. Here we go. All right. Tell us about this one.
So I was trying to get a occultation of Mercury by the moon, but it turns out I was a little too far east and there are a few too many trees in the way to actually see it. But I still did get this nice conjunction of them. This was a real emotional roller coaster because when I was first setting up, there were clouds right in the wrong place. Turns out I was looking slightly to the left of where I should have been. And then just as I'm packing up my camera, thinking it's not going to work, there it is. And so I put everything back together. And this is a video comprised of 114 frames taken 5 seconds apart, 1 second exposure each. So this is a little under 10 minutes. And each exposure is 1 second long at ISO 3200. And I just took this from a bridge over a river near my house. And it's where, if you want to know exactly where it is, just look on Google Maps for US 1 crosses the Tomoka River in Ormond Beach. And yes, I took this 3 feet from cars on a US highway that were buzzing by me at like 55 miles an hour, which is why the image shakes every so often, or I bumped the camera. And I'm amazed this came out as well as it did, given all of that. So that's my image.
Nice. I mean, Justin was talking about how we deal with what the conditions that we got, right? So like you were by a highway and you still managed to capture a moon, and there's some earth shine there too. So even in a
Yeah,
one shot. So yeah, very cool, Luke. Thank you for contributing. That's very cool. I was hoping somebody had done the Moon Mercury conjunction.
I'm glad somebody did.
All right, Massimo Reynolds. Yeah, you're here.
Mm, Oh, you hear me?
Yes, sir.
Hello?
Okay.
All right. Hey, everyone. Uh, I have some lovely moon pictures for you, but actually it took me a really long time to have the opportunity to take these photos. I'd consider myself like a amateur astrophotographer for like about a year. I remember my like very first photos back in March 14th of 2025 when I took the lunar eclipse photos with my phone, and I had a little you know cheap Vivitar telescope. That was like my very first like moments, and even with that telescope, it turned out pretty well. And then I came around this March, and March 3rd, I took some more photos. And throughout last year, I kind of used the remote C Star, which is if you don't use it, if you don't know what it is, go to the groups.io. It's a really helpful tool, and you get a lot of good shots of like distant objects, even right from your old home. Even if you're like in a suburban area where there's a lot of light pollution, it's in Texas, and it'll take a lot of good shots for you. And then for the all the photos you see here, I actually still use my phone, and I use the Dobsonian 8-inch, and um, I was given it to by the current loaner telescope chair, Paul. I think he might be here. Thanks, Paul. I'm using it a lot, and I'm really enjoying it. And I originally had the Mead, and it was dysfunctional. But there's one time I went to Geneva, and he loaned me the Dobsonian, and I saw the moon like very like crystal clear for the first time, and I was like really hysterical. I know it was great. And then I also used the Observer's Handbook and the calendar I won at the raffle party from last Christmas. But all these photos actually just use my phone. I didn't need any fancy software. I didn't need any of that. I just went to the backyard. It was last day of March. I went to my backyard. I took out my Dobsonian, and I just took really good pictures with my phone. And I had to be very careful with actually taking pictures of it, because if you look like through a really big telescope up at the moon with their just no filters or anything, you're basically kind of blinding yourself, because the moonlight is that bright, it's that intense, and you need to actually filter. But I kind of had to be risky with it, because the filter itself kind of like doesn't it kind of like doesn't really get that like crystal clear like shine that the moon naturally has. So I kind of like had to be risky with it, and I use my phone and kind of like move it with the lens without actually looking at it myself. But here you have some really pictures of really prominent features of the moon. We have the Copernic, the sorry, we have on the top left, we have, I think is a really good photo. I kind of like use my, artistic mind of kind of doing it. It's on the eastern side of the moon. You have a bunch of nice little Mara right there. In the top middle, we have Copernicus crater, which is kind of like dead center of the moon. It's really not hard to miss, if you have like a kind of normal telescope. And then top right, we have the yeah, wrote it down. I'm not very that good at memorizing features of the moon, so just give me a second. Okay, we have the uh, Tycho crater. Yeah, it's around kind of like the South Pole. And then bottom left, we have, I believe, give me a second. Yeah, we have the Sea of Serenity, which is very important, because around, I think, kind of the eastern edge, that was the moon landing of Apollo 17. That is where the last men landed on the moon. And actually, a couple of years, they won't be the last men, because Artemis 3 is the planned actual moon landing, the next landing to the moon. So that'll be really exciting. And then bottom middle, we have the Sea of Pisces, and that's kind of like towards the east. I like it. It's this nice little like puddle. It's not really a big splotch. And of course, I think my favorite is the bottom right, which is the full complete moon and all of its spectacle. Nice and bright. And yeah, all these pictures, I just took with my phone and my telescope who I was lended to, thanks to Paul. And this just proves to you that you don't need the fancy technology. You don't need really expensive software and post processing. You can really just take your phone and a telescope and take some really cool pictures.
Absolutely. Good job, Massimo. Thank you so much for contributing these.
Yeah, no
We all
problem.
start somewhere, and this is a perfect start.
Hmm.
Right. Next up, we have James Ebbs. You hear James? Well, he contributed this on groups.io. It's M16, the Eagle Nebula, and I think this was taken at a one of those remote telescope places down in Australia, if I recall from what he said on there. But it's a very cool image. Nice, not lots of nice detail there on the pillars. So thank you, James, for contributing that. It's a very cool little image. Jeff Merrick, I saw you here.
Yeah, I'm here.
Right,
Yep.
there you go.
Well, we all know what galaxy that is. This was taken with my camera and 200 millimeter lens. And there was 27 subs at 30 seconds. So not too many subs. Uh, um, but anyways, I thought that was a nice picture of the galaxy. So I took it. Usually I
Great.
try fainter objects, but this time I tried M31. So,
Nice.
okay. This is the Cygnus wall. Again, like I don't have 40 hours to image things with the integration time of 40 hours. And in Florida, Portal 5 or 6, I'm lucky to get, a couple of days a month. So I took this a while back. This was taken with the H alpha O3 filter. The sub exposure was like 5 minutes, and the number of subs were only 35. So the integration time was only about 3 hours, I think. Um, not long, but still it captured quite a bit of detail. And this was a pretty good photo. I don't think, I mean, you always capture more detail. I mean, the SNR goes up when you have more subs, but I don't know if that's worth the effort, and in Florida at least. So
Yeah, I mean, it's all about the time that we have, right? Like we've had January was very nice and February was okay, but March
yeah,
and April so far,
April's been terrible, and
it's been bad.
oh, I don't know when we're going to get the next clear night. Maybe this weekend.
Maybe this weekend, maybe
Mhm.
if we're willing to sacrifice, deal with
Lots
some
of
transparency.
detail, lots of detail in that image. It's a H alpha filter, and you see hydrogen all over the place, and you
Yeah,
see, you know, structure details and everything. So,
yeah, it's a good one.
mm,
Very nice, Jeff. Thank you for that.
okay.
James Leiter, Jim, I don't know if he's here. I don't see him. If you are, Jim, speak up. This was taken at Geneva on March 20th, one of our most recent dark sky nights. It's M51, and it was taken with a William Optics 120, an ASI 533, and the whole thing running with NITA and processed in Serial. So not a bad M51, Jim. Thank you. Pretty good. Mickey Huffman. You hear Mickey? I don't see you there. So if you are, please speak up. Otherwise, it's also an M51. We've got an M51 party going on right now. Um, so here's his shot of M51. I don't remember the details, but it's a pretty good close-up of M51. So thank you, Mickey. And he also submitted this one of the sombrero. It's a very good image of the sombrero. I really like this one. The detail on the outer structure there is really good. So good job, Mickey. Michael Sneed. Oh, yeah, I don't see you there. Okay, Michael. Here's his image of again M51. I don't think I don't think he sent in his details on it, but this is a really good shot of M51. I really like the star color he's got going on here. So this was a good one. Thank you, Mickey. I'm sorry. Thank you, Michael. Here's mine. Here's the one I submitted. I took this down at the Winter Star Party in the Keys in February. This is LDN 777, the Baby Eagle Nebula. It's just a whole bunch of like the dark, dusty stuff that's going on around in Taurus near like the Pleiades and in the direction of the California Nebula. So the blue stuff you see off to the side there, that's actually sort of like the glow from the Pleiades sort of bleeding over there. So I would never be able to take this image from home. So that's a good example of what Justin was talking about. Like there's no substitute for dark skies. And I think this was about 10 hours with a Red Cat 51 and a Player One Zeus. John Sasson, I know you're here.
Yeah.
Here we go. This was a last minute submission. I almost didn't see it. So there you go.
Yeah, I finished it last night, so that's why.
Nice. Very good.
So this was M78. So total 40 hours, 30 of that, 28 of that was luminance, and then I only got about 4 hours per color channel. I wanted to do a little bit more. That was just all I got. And then add insult to injury, I wasn't checking my sequencer, and I didn't take any flat for the green, and I had these giant dust motes, so that was kind of a pain to fight through. But still turned out semi-decent, so I'm still happy with it. Probably
Not bad.
wait till later this year to add more data to it when it comes back up for long enough.
Absolutely. Yeah, you can
So
always add
yeah,
more.
that's the beauty of it, right? You can pause it and go back to it later in time.
Very nice.
So, work in progress.
Work in progress. All of our images. Isn't that one of those famous quotes about like things like that? Work is never done, it's just abandoned. So yeah, that's sort of how we roll sometimes. Pete, I think I saw you here, right? Yeah, there you are. And
Hey,
Pete's
Wes.
our remote observing chair. He gets to play around with the Sea Star we have out in Starfront in Texas all the time. So he sometimes processes our Sea Star data out there.
Yeah, Wes. So this is I focused this was done in February, and I was focused on long integration, which I thought it was long integration until tonight's presentations. But this is a little over 6 hours of usable frames on M53 from Starfront, processed in just real light processing and PixInsight. But again, this is 60,000 light years away, so it's one of the furthest star clusters here in the Milky Way. So I think it did a nice job of pulling it in.
Yeah, I agree.
And this was a project on M81 done in March. And this was around 7.5 hours of usable data that came out of this. And this, for whatever reason, I don't know if it was low in the sky or what happened, but I had to actually manually process this data. So it took quite a few hours to actually get all of this to stack and align, kind of the comments that I heard earlier. But I guess I don't have a powerful enough machine, but I think I spent about 30 hours total just to get it to actually stack. The FBPP wouldn't work correctly on it, but M81, I just was curious to see with a few hours on the Sea Star out there at Starfront, how that would come out.
Well, I think that turned out pretty darn good. You said it was about 7 hours with a C star, and I'm seeing the hints of some of the IFN there. There's that little loop that's
Yeah,
right above it. So that's pretty awesome with
yeah,
an uncooled camera.
yeah.
So
I mean, and for whatever reason, I don't understand why FBPP, which is significantly faster, it just rejected almost all of the subframes. But
some,
yeah, it came out nice.
yeah, our stuff works most of the time, and then
Yeah.
sometimes it doesn't. Thank you, Pete. Awesome.
Yep.
Again, Pete here is our remote observing chair. So if you want to use this C star out at Starfront, please get on our groups.io, contact Pete, and he'll get you set up with this.
Yeah,
All
everything you
right.
take gets uploaded the next day, so you can easily pull it down.
Absolutely. We have our archive, so yep, all the data gets saved. All right, John Starr, saw you here.
Yeah, good evening.
Hey, man, here we
So,
go.
yeah, I think so tonight was really, really fantastic night between Justin's presentation and all of the member submissions. It was really, really solid lineup tonight. So really fun to see a lot of the images. I feel like I missed out on an opportunity to shoot M51, so I'll have to do that next time around. So yeah, so this image, I began shooting this as a supernova remnant in the constellation Auriga, and began shooting this way too late in the season. Started shooting this in early February. Really, probably should have started shooting it in October or November. So I only had a handful of hours every evening. Ultimately, about 95 hours on this target. About 35 or so each in hydrogen and oxygen, and then another 7 to 8 hours in each of red, green, and blue. Shot this with an ASCAR FRA 500 reduced to f3.9 Antlia filters on an ZW ASI 2600 mono and a ZW AM5 mount hosted at Starfront. So hadn't seen too many, although I was checking out Justin's website while he was talking, and I saw a much, much nicer image of this particular target. So I will have to revisit this one next year and see if I can get some more data. And so yeah, but this one was definitely a challenging target. I processed it like most folks. I processed it probably 8 or 9 times before I finally found one that I actually liked. So
Cool.
yeah.
Thank you, John. And this is one of those ones that when I emailed you, it's just like this is the kind of image that you see these edge case supernova remnants and you're like, I just could not possibly even think about doing that at home. You have to have that portal one and like 50 to 100 hours to get something like this. So that's super cool. Thank you, John, for throwing this one in here. And that's it for the main part of the meeting. One thing I did want to mention, I didn't include it in our club news. We do have the Omoa event on April 25th. So if you want to participate in that, please do. We need volunteers. So contact Isabel or on groups.io to look for more information about that. So, okay. Thank you, everybody, for attending the meeting. This was an awesome meeting. Thank you so much to Justin and everybody that submitted an image for the astrophotography showcase. So thank you so much. And if you want to stick around and chat with Justin, again, I think he's going to hang out and we can just chat about astrophotography and astronomy. So thank you to everyone and clear skies.